Section 1.3, atomic theory. This is the meat and potatoes of this unit. In fact, this is the final topic of this first chapter. But this is the basic building blocks of the universe. This is what quantum theory is based on, if you've heard that term, except quantum theory is really weird. We're going to start off actually keeping it basic with what we call atomic theory. You may even see the root word atom. We're going to talk about atoms in there. First, it turns out there was some Greek philosophers, and they were around 2,500 years ago, and they simply asked a question. They said, what is everything made of? What is everything made of? And here's what they argued. They said if you kept dividing, so take a piece of wood, cut it in half, cut that half in half, cut that half in half and half, cut that half in, they said if you kept doing that, eventually you would end up with a tiny, tiny, tiny piece, a piece that was so small you could never split it up, a fundamental piece. And they called that atomos. They were both right and wrong. They were on the right track in that in many substances, if you can somehow cut them apart, you can reach a final smallest fundamental piece. But that final smallest fundamental piece is incomprehensibly small. I have a math degree and I can't visualize it. And Aristotle, one of the greatest minds at the time, said they were wrong. Aristotle said that all matter was made of different combinations of air, water, earth, and fire. And because he was influential, the atomos theory was discarded for the next 2,000 years or so, and no one made any progress. So I wrote here a reminder to think for yourself sometimes. People still wanted to know what's everything made of. People still wanted to know what's everything made of. Then came the alchemists, A-L-C-H-E-M. By the way, can you see the word chemist or chemistry starting to appear in there? In medieval Europe, when there was like knights and kings and dukes and barons and all that, they weren't quite so interested in figuring out what everything was made of. Instead, they wanted to turn lead into, what do you think they wanted to turn it into? Gold. Why lead? Because lead is heavy and gold is heavy. So they figured, hey, maybe somehow there's something the same about them, maybe with some magic and witchcraft. Or actually, they were trying to do it in a lab, but a very crude lab. Maybe we can do that. Can't. But, so they didn't succeed, but they did discover lots and lots and lots of new elements and new things along the way. Oh, turns out if you mix this and this, it'll blow up. Turns out if you mix this and this, they found out all sorts of stuff. But things kind of stagnated there until around 1800 we have John Dalton. Okay? John Dalton came along. He showed why the alchemists had been wasting their time for hundreds of years. He showed Aristotle was wrong. And while Dalton's theory has since been refined, in fact, at the end of this lesson, what I'm telling you has since been refined, but we're not going to get that far. Oh. So John Dalton's theory has been refined, but we're going to start with what he believed, which was only partly right. We're going to go to the next scientist that built on what he believed, which was more right, but still only partly right. And eventually we're going to get to where we currently are, sort of. Here's what he said. He said, the Greeks way back when were right. You can break stuff down into fundamental components called, oh, need the pen back, atoms. And in his model, an atom is a solid sphere or ball. In other words, to John Dalton, in his mind, he was kind of imagining this, except I know these have air in the center, they're hollow, a tennis ball. Imagine it solid, so like a lacrosse ball. I think that's what an atom is. No, but it was a start. So I have a lovely picture for you here. Mine is in color, yours is in black and white, but use your imagination. Okay? He said that all the different elements on that periodic table up there behind Nick, all the different elements are different little atoms. He said a gold atom would be different from a hydrogen atom, would be different from an iron atom, would be different from a copper atom, would be different from it, would be different from it, would be different from it. He said all of the different atoms were different little tiny spheres. So here's what he said. This was a good start. All matter is made up of small particles called atoms. And he said atoms cannot be created. He said they can't be destroyed. And here was the key thing as well. He said, Mason, they can't be split into smaller particles. He said, this is the smallest a thing can be. He was wrong. We now know actually you can go smaller, but it was a start. You're nodding your heads, kind of seeing where we're going. He said, all atoms of the same element are identical in mass and size, but they are different in mass and size from the atoms of other element. In other words, he said, if you have a piece of iron, if you could somehow with magic and witchcraft pull out one iron atom and replace it with another iron atom, no one would know the difference, because iron atom, an iron atom, and an iron atom, well here, he would say an iron atom and an iron atom are indistinguishable. There is no way in the universe you can tell them apart. On that, he was mostly right, although we've since learned not quite. By the way, you're going to hear me say that a lot for the next while. I can show you the basics of chemistry, but as soon as you go into complicated chemistry, a lot of the things that I tell you are rules suddenly get broken. Nuclear and radioactivity, but for the most part, what I'm teaching you, Trevor, will be right. Okay? So, iron atom, iron atom. Oh, but then he also said it would be a different size, say, from a hydrogen atom. So this might be a hydrogen atom. I know hydrogen would be smaller. Iron is heavier. He argued it would be a little bit bigger. Gold is even heavier. He argued it would be bigger. And by bigger, I still mean you need to imagine these unfathomably small, so small you can't wrap your brain around them, unfathomably small. Small. No, smaller than that. Small. Okay? What else did he say? Compounds. There's the word. Compounds are created when atoms of different elements link together in specific ratios or proportions. Don't write this down, just watch. That's the symbol for hydrogen, H. That's the symbol for oxygen, O. Those would be atoms. Then he said, oh, you want to form water? Water, you need 2 hydrogens, 1 oxygen, add a little bit of flame. It turns out you need some heat to get the reaction going because those are both gases. But if you have hydrogen gas and oxygen gas, you shake them, throw a match in there, there's going to be a big boom, a very spectacular boom, and at the bottom, you'll see some water when you're done. They will have combined. But they have to combine in a 2 hydrogen, 1 oxygen ratio. And he was right on that. He was not right on the fact that we can do more with atoms than that. So, following in Dalton's footsteps was J.J. Thomson in 1897. So in 1897, J.J. Thomson discovered negatively charged particles. And these charged particles were, smaller than atoms, which suggested that maybe atoms can be broken down even further. In fact, later on he called these electrons, from which our word electricity comes from. All electricity is trillions of electrons getting forced through a wire. And so he realized that atoms are made up of much smaller particles. Instead of a solid sphere, now J.J. Thomson was British, and so he advocated something in Britain, a dessert in Britain that was familiar to the British, which isn't as familiar in North America. He said an atom was like plum pudding. He said, you imagine a bunch of pudding, and inside the pudding, there's little pieces, the plums all over the place. He said the plums are the electrons, I think, and the pudding is the atom. But he said they're smaller chunks. Because we don't have plum puddings, I'm going to use the analogy of a chocolate chip muffin, because I'm going to assume you've all seen that. So in his model, electrons, which are the chocolate chips, and electrons are negatively charged, are embedded in a positively charged dough ball, the rest of the muffin. So I wrote here, J.J. Thomson used a plum pudding as his analogy, so this is often called the plum pudding model of an atom. He was getting closer. First of all, he recognized that if part of the atom was negatively charged, electrons, but overall the atom was positively charged, that must mean there had, was neutrally charged, that must mean there was some positive charges that we hadn't discovered yet, because the only way that you can get a negative to add to 0 is to add a positive to it. That's pretty clever. And he knew that electrons are spread out. He kind of knew that. You've all turned the page. Put your pencils down. Look up. So you can expect that I might ask you to describe a little bit the plum pudding model of the atom, and you can use chocolate chip cookie as your analogy, chocolate chip muffin as your analogy, cherry tart. You can use plum pudding, but we're not British. That's not a dessert that we're all that common with. Hey, he's moving in to stay. Excellent. Next, we have one of my favorite scientists, Ernest Rutherford, often called the father of nuclear physics. In fact, if you look, many of his grad students, the students that studied under him, have names like Geiger counter. There's a whole bunch of radiation type things that are named after his students because he was on the cutting edge of figuring out how radioactivity worked. So, he was a student of J.J. Thomson, so there's kind of like a little teaching tree here. And he did a very, very famous experiment. Expect to have to describe it on a test or a quiz. This will be, I guarantee you, a written question on your test. I will ask you to explain and describe the experiment. So you make a little note, put a little star next to here, whatever you want to do in your notes. But don't worry, we're going to be talking about an awful lot. Oh, proud Canadian moment. He did this famous experiment at McGill University in Montreal. So we have a little Canadian history there. In fact, even though I think he was born in New Zealand, and he had British citizenry, I think Canada tries to claim him as our own as well, because, yeah, Canada, you did it here. Okay. What did he do? In 1909, he exposed a very thin, how thin? Only several dozen atoms thick, thin, very thin, sheet of gold. Remember yesterday I said gold was very malleable. You could beat it very, very thin with the hammer. That's why he was using gold. You can get it really thin. To a stream of high-speed, heavy, all of you underline the word positively, please. This is going to be important. Positively charged particles called alpha particles. Put your pencil down. Look up. So let's write that down. Alpha particles were like tiny bullets, but think bullets the size of bowling balls. On an atomic scale, an alpha particle is incredibly heavy. When he put a detector around gold foil, it would glow for a split second whenever an alpha particle hit the detector. If you want the fancy word, it would phosphoresce, but I'll just say glow because that's less intimidating. Okay. So here's a picture of the, yours is black and white, but you can still figure it out. He had a source of alpha particles. Most of them would go straight through, so there was a big dot right there. Most of them would go straight through, but every so often, every few million or so, one would bounce off. What did this mean? So the results showed that most of the alpha particles went straight through the gold atoms. And this made sense, or the conclusion was most of the atom is made up of empty what? Space. And it is literally empty. There's no matter there. Don't think like, oh, there's air. There. No, because even air is too small to fit in there. I guess you could say it's sort of a vacuum, but there's nothingness. Nothing there. However, he was astonished to see some alpha particles rebounded. So first of all, this meant that they had hit something really massive. Why? Because the alpha particles were huge. For them to bounce off something, they had to, otherwise, I mean, let's be pretty clear. If I could fire a bowling ball as fast as a bullet, it's going through almost everything, right? Unless it hits something really massive. And there's your analogy on the atomic scale. Oh, yeah.
How big was the actual thing that was
I have a video that's going to show you, and the answer is going to be so small that you can't wrap your... honestly, if you're asking for a number, any number I tried to give you would be meaningless. 0.000000000 meters. 0.1 meters. Ridiculously small. And I'll show you a video that's going to give you some analogies. We're going to ask, what if an atom was the size of a football stadium? How big would the nucleus be then? That's going to be our analogy. And the answer is still going to be, holy smoke, stinking small. Okay? But it also meant this mysterious massive object must be, why? Hardly ever hit it. So if you're looking for why here, hardly ever hit it. And if you're looking for why on the line above, because alpha particles are really heavy. So if they bounced off, they must have hit something really, really heavy. I can give you a better, if you ask me, Kevin, in a couple of weeks, I can probably give you a better explanation once you have more sciencey vocabulary and I can use words better than really small, but not yet. Duh! He had discovered the nucleus, the very, very, very tiny, very, very, very dense, positively charged center of an atom. Every atom has a nucleus. A hydrogen nucleus is different from a helium nucleus, is different from a copper nucleus, is different from a nickel nucleus, is different from a neon nucleus, but it turns out that's going to explain a lot of how the universe works. And then the other thing that's going to explain a lot of how the universe works are how the electrons behave. I think he won a Nobel Prize for this, I think. A decade later, he actually established that there was two things in the nucleus, two different particles. He found a positively charged one, the proton, and then he also found a neutrally charged one. Katie, I heard it. How can I remember that neutrons are neutral? How can I remember that neutrons are neutral? You know what? I got nothing. I'm a lousy teacher. You'll have to figure out your own way. Can't come up with anything. How can I remember that protons are positive? How can I remember, Mr. Dueck, that protons are positive? You know what? I have no idea. You have to come up with your own thing. Hopefully you figured it out there, yeah? Put your pencil down. Neon lights, which you have seen all over the place, are a great example of this. Okay? Neon lights. When electricity is added to neon gas, the electrons pick up some of that energy and they jump to a higher energy level or shell. They don't want to stay there. By the way, I'm saying they don't want to stay there as though they have will and thinking and consciousness. They don't, but we're often going to say, you know, protons want to behave this way. They don't have brains, but it's just an easy analogy, okay? It's just the laws of the universe. So when those electrons drop back down to a lower level, they have to release some of that extra energy. This extra energy takes the form of a photon of light. That's what's going on in these fluorescent tubes here, by the way. It's not neon, it's a different gas in there. But all we're doing is we're adding electricity to the gas. We're exciting the electrons. They're bumping up an energy level. They're falling back down. And when they fall back down, they have to get rid of their energy somehow. Let there be light. Inside the atom. So, the atom is the smallest particle of the element that retains the same properties of the element. So we thought for a while that the atoms were as small as it goes. We now know that atoms are made up of electrons and protons and neutrons. But when I talk about an iron atom, all iron atoms look the same. When I talk about a copper atom, all copper atoms look the same. We now know that there are smaller particles. We call them subatomic particles. Sub meaning less than or below, or in this case, Ibrahim, smaller than atoms. You're going to need to know these three. We're going to be flogging these to death. First one, the proton. And then I have blank charged. Proton. What was that charged? Are you positive? Okay. Then we have neutron. What was the charge on a neutron? Well, the word we use is neutral. Really what that means is no charge. Mr. Dueck, how will I remember that a neutron has no charge? It's neutral. Mr. Dueck, can you think of a good way to remember that a neutron has no charge and is neutral? I'm sorry, I have nothing for you. I apologize. I suck as a teacher. You'll have to figure out something on your own. Then we have electrons, from which we get our word electricity, and they are negatively charged. An atom walks into a bar and he says to the bartender, "I've lost an electron." The bartender says, "Are you sure?" The atom says, "Yes, I'm positive." Oh, they only get worse. Okay. All three particles have mass. They all weigh something. But the protons and the neutrons have way more mass than an electron. In fact, electrons have so little mass that we're going to pretend they're zero, just because you'd only notice them making a difference if we carried our calculations out to 19 decimal places, which we could. So, turns out protons and neutrons contain 99.9% of the mass of an atom. That remaining 0.1% is the electrons. We're just going to really ignore that mass for the most part. Almost done. And this is going to be kind of a repeat, and then I got a couple of more cool videos to show you. A good stretch. You awake? I know I've been talking a lot, but we've had little video breaks. So, turns out electric charge comes in two types. Positive and, altogether, negative. By the way, you're going to see I tend to occasionally in lessons repeat myself. Repeating myself occasionally will happen in lessons. You're teenagers, so I find that repeating myself is helpful. Catch that? I don't know. Which ones have a positive charge? Protons have a positive charge? Boy, I wish there was an easy way to remember that. Now, be careful. Which ones have a negative charge? Now, the only problem is sometimes kids want to go, oh, neutrons are neutral. Electrons. I'm not going to write the word protons or electrons again. Too much writing. In fact, I'm going to show you we have symbols for them, lovely abbreviations, and I think I've told you already that I tend to abbreviate. So, each charge has the same size or magnitude, but opposite sign. In other words, the charge on an electron and the charge on a proton, they're each as big as each other, just opposite signs. So if you add +1 and -1, you get 0. If you add 1 proton to 1 electron, you get a charge of 0, because they exactly cancel each other out. The fancy word for a charge of 0 begins with the letter N, neutral. You can see this little chart? See this little chart? I like this chart. I like this chart. I like this chart. I like this chart. Why would I say that? No, it's not really because I like the chart. Why would I say that? You're going to see it on a test. Why would I say that? Did you hear me say that I was going to say it on a test? You're just kind of student that tends to notice when a teacher emphasizes certain things. Brooke, that'll serve you very well. So I like this question. I like this question. I like this question. Pick up on the hint there, please. Proton. What would be a good symbol to use for a proton? We use a lowercase p, and then we actually put a little plus sign up there. We call them p pluses. Or if you write p plus, I'll read out proton. What would be a good, we're going to go down, what would be a good symbol to use for a neutron? One's right. He said minus, she said 0. Who's right? 0. Neutral, right? Kind of looks like no, but not. What would be a good symbol to use for an electron? E negative. From now on, you can write that anywhere, and I will clue in you mean the word proton or neutron or electron. I won't take marks off. Okay? We're going to skip the relative mass in a second. Electric charge. Positive, 0, negative. We're nearly done, yeah? Yeah. Relative mass. Relative mass. It turns out that protons and neutrons weigh almost the same. Now, we measure these in what are called atomic mass. You know what? Don't worry about the number. But it turns out a proton has 1837, a neutron has 1836, and an electron has 1. In other words, a proton is 1,837 times heavier than an electron. A neutron is 1,836 times heavier than, you know what? We're just going to pretend, Danielle, yeah, that neutrons and protons have the same mass. That's pretty close. And we're going to pretend that an electron has no mass because it's really small. But if you want that, there's their ratios. I probably won't make you memorize this part, but certainly that, and their location. Where are protons and neutrons located? We're going to use the fancy smancy new word. If you say middle, I won't give you full marks. But if you say nucleus, my little math nerd heart will go pitter-pat. Where are the electrons located? Outside in, and there's a word that begins with letter S, shells. And it turns out that there, if you understand how those shells work, you can now predict the universe. You can predict how compounds, how different atoms will combine. That's next chapter. Let's talk about the nucleus. It's a tiny region in the, hey, you figured that out. And it's really mind-bogglingly small. Smally. There you go. Really small. Yeah, smally, that might be a word. Right? When Nick stands next to Cole, it's kind of smally. No? Okay. Sorry. Okay. And then I have the nucleus is always blank charge. What would the charge be on a nucleus if it contains the protons and the neutrons? What's the charge on the neutrons? 0. What's the charge on the protons? So what would 0 plus positive be? You know what? It's always positively charged. since that's where the protons exist. There is one atom, one type of atom that has no neutrons, and that is hydrogen. There's a reason why hydrogen is the first element on the periodic table. It's the simplest possible element. There's a reason why hydrogen is the most common element in the universe, because when the Big Bang occurred, hydrogen was the easiest thing that formed. Everything else is more difficult. So every atom past hydrogen also has neutrons in its nucleus. Protons and neutrons are held together in the nucleus. Normally they can't enter or leave it, but we can force feed it. That's what the Large Hadron Collider does. And when you're talking about radioactive elements, part of what you're talking about is sometimes they shoot out nucleuses, but we're going to pretend they're stable because radioactivity is tricky and cool. Nearly done? So, in situations where we can change the nucleus, we call that radioactive. So when you hear something is radioactive, what we're really saying is the nucleus is decaying somehow, changing somehow. By the way, turns out far more things are radioactive than you realize. Don't freak out. Electrons. They occupy special regions called energy levels, or our magic word of the day is shells. Now, protons and neutrons make up almost all of the mass of an atom, but they're so small, it turns out the region that the electrons occupy makes up 99.99% of the size of the volume of an atom. So electrons, even though they're really, really, really light, Alex, they take up lots of room. You awake? Okay, a little worried you might be drooling there, kind of head. You're good, okay. Each electron occupies one whole energy level at a time. It's not like a planet orbits around a star, which is why in fact, you know what? You can cross out the word orbits now that you've written it. I want to discourage you from using it. They still like to use it in the US, and in some of the videos which have good graphics that I'm going to show you that were made in the US, they're going to use the word orbits, and every time you hear that in your mind, draw a line through it, shells. What are electrons? This is one of the most complicated things in the universe. I can't tell you what electrons are. I'm going to say we're going to pretend they're like little tiny particle ball things. They're not. It's more like a spread out cloud of negative charge that exists in the whole region all at once, but it's actually way stranger than that. If you're a science nerd, do a YouTube search for quantum physics explained or quantum physics explanation and be afraid, because electrons are weirder than weirder than weird. Having said that, we've been able to build all of our technology around controlling them, so yay!